Hi, and welcome to Lecture 2A for Physics 151. This topic is SI, or metric system of units, and the metric prefixes that we use with those units. In addition, we'll discuss some dimensional analysis that we can do with those units, and finally I'll talk about the way I convert between different units for a physical quantity. The related materials are practice problems on tutorial 2A and the solutions that are uploaded, and then your assigned problems on homework number 2. Most of homework 2 is about units. Now, I realize that many of you are already really familiar with this topic from your other science classes, and if that's true, then feel free to skim through much or all of this lecture. Feel free to do as many of the tutorial problems as you need, but if those look really familiar, then skip those and go straight to the online homework, and which are the problems that are for credit. Let me start by just saying that it's a really important habit and an essential practice throughout the sciences that we always label all of our numerical or quantitative values with the units that they should have. This not only tells us what sort of physical quantity they are and the rough sort of size of that quantity, but also it prevents us from making algebraic or logical mistakes, like adding or subtracting quantities that have different dimensions and that are different physical quantities. That's forbidden, by the way. Mathematically, you should never ever add or subtract a mass and a time. You should never add a length to a pressure. You can multiply and divide those, but those should never be added or subtracted from each other. Now let's sort of think about all the different units that we encounter as we do either the homework problems in our physics and chemistry classes, or as we measure things in the laboratory or in nature. So pause this recording and make a short list, either mentally or on paper, of some of the different units that you remember encountering. I'm sorry, not units, but physical quantities. For example, maybe you've measured the time it takes for a pendulum to swing, or maybe you've measured the pressure in a chamber in the room. Okay, pause now. All right, now look over the list of physical quantities that you've made and try to identify for yourself, do some of them look like they're more basic and fundamental than others? And do other ones on that list feel like they are composed of more fundamental and basic units? So in other words, do they seem like they're compound, right? Or derived from those more basic quantities? An example of this might be speed. A speed, if you're measuring like the speed of the glider car, the little gliders that go on the air tracks that you're going to use in lab later this semester, then a speed is a length divided by a time. So we know that speed doesn't seem to be fundamental. It seems to be built out of more fundamental units. Whereas length or time, those don't seem to be composed out of anything more basic than they are. They seem pretty basic themselves. Well, folks who sort of thought very hard about our metric system agree, and they identified 7 quantities that they call the fundamental or base quantities of the SI system or metric system. SI stands for Système International. Here they are listed on the left-hand side, and it's a good idea to sort of memorize what these base quantities are, these fundamental quantities. The ones that we're going to use the most in Physics 151 are the ones related to mechanics, of course, and then toward the end of the semester to thermodynamics. Briefly, we might mention moles, and then current is used in Physics 152. Now, just as a brief editorial comment, I think it's a little strange that they chose quantities that are actually kind of complex. Like temperature is actually sort of related to the average speed of particles in a substance. And current is definitely charge divided by time. So why didn't they use charge as the fundamental unit? Well, I think that they have their reasons that I'm just not aware of, and that's fine. So, but these first few definitely seem like they are really fundamental quantities of nature. Then over here on the right, we have the units that are used in different unit systems for those fundamental quantities. So in the MKS system, we use meters, kilograms, and seconds for these three most basic quantities here, and hence the name MKS. It comes from the first letters of these units. The CGS system uses centimeters, grams, and seconds for those same three fundamental physical quantities. It's traditional to capitalize MKS and leave CGS lowercase. Then there are non-metric systems like the British units or imperial units, which are used in the United States. So here I have some of the distances and lengths that we use. We use seconds also for time, just like the metric system does. And then we have these weird units for mass and temperature. Let's think for a moment about these base units of the MKS and CGS systems. So I've listed them here. It's important for us to, as future scientists, to develop an intuitive feel for what roughly the size of these quantities are. And I know that growing up in the United States, we mostly use British units in our daily lives. So a lot of us don't grow up, thinking about kilograms or meters very much. But I know you've taken a lot of science classes. So what I'd like you to do is try and identify one or two things that from daily life that have about the same size as a meter, or that take about the same time length as a second. So pause the lecture now. Okay. So I've listed a few here. Some of these I came up with myself, and some of these I borrowed from section 1.3 of our textbook. Notice that the MKS units, which are written in purple here, they really are right in the mid-range of everyday human experience. Meaning, a kilogram is about the mass of things that we carry around all the time. A second is about the time between heartbeats. Meters are about the size of a person. So as a result, these are really convenient units for daily life, and most countries have adopted them for everyday use. So when you go to the supermarket, most packages are labeled with those quantities. It does sort of raise the question, though, if these are sort of in the middle of human experience, what really is the sort of full range of meters, the full range of seconds and kilograms that we have measured ever? Right? Or that seem to even occur in nature or in the universe. Well, let's start with the question of lengths. So here's a nice diagram from our textbook that sort of shows the full range of lengths that we talk about in the sciences, or that we've ever had occasion to measure. So the size of a proton or a neutron inside the nucleus of an atom is about 10 to the minus 15 meters across in diameter. The whole nucleus is about another order of magnitude bigger than that. And then we have atoms, and then we have very small objects like cells and so on, until finally we get to people, and the scale of humans is on the order of about a meter. And then we have planets, stars, distances between planets and stars, and then finally distances between galaxies, to the range of the entire observable universe. This is the horizon that we can observe. It's the farthest that light has had time to travel in the age of the universe. Notice that this is over 40 orders of magnitude, over 40 powers of 10 between the largest and the very smallest of things that we deal with in the sciences or that we've ever observed. There's a beautiful sort of cosmic zoom, if you will, that was turned into a film. The classic version from 1977 is right here, powers of 10, and there are more updated versions of it that exist as well. Or there are applets that you can control yourself that allow you to sort of step through these orders of magnitude in the universe. There is one point I want to make, and that is there's sort of a range. If you, while solving a physics problem, ever wind up with values that are well outside of this range, like 10 to the negative 35 meters or 10 to the 58 meters, then you should realize that that's not a physical value. You can write it down mathematically, but it doesn't really have physical meaning because it lies outside the range of anything that we know of in the universe, and therefore it's probably not going to be the answer that you're looking for your problem. Double check your work because chances are there may be a math error somewhere along the way. There are a couple unit names that you should also memorize in addition to the basic meter, and that is there's the micron. Now the micron is actually a metric. It is a metric unit. It's 1/millionth of a meter, and that's 1 micrometer. But the nickname micron is used so much for micrometer that you should memorize and recognize it by itself. And then the angstrom. The angstrom is 1/10 billionth of a meter. It's 1/10 of a nanometer. In most modern publications, nanometers are used instead, but people still talk about angstroms a lot when they're talking about wavelengths of light, and if you look in slightly older publications, they're very, very common, so you should know what it is. The convenient thing about an angstrom is it's basically the diameter of a hydrogen atom. It's to within like 2 sig figs. That's about the diameter of a hydrogen atom, so 1 angstrom. It's a handy thing to remember. And I hope that as you proceed in the sciences, you'll develop a little bit of an intuitive feeling for how big, in meters, how big things are. Like how many microns is a typical bacterium, or what is roughly the distance in meters, between the sun and the Earth. Speaking of which, astronomers like to, because meters become unwieldy for so many of the distances we use, we like to use these other units over here, like astronomical units, AUs, for distances between planets, and light years and parsecs for distances between stars, or kiloparsecs and megaparsecs and gigaparsecs for distances between galaxies. However, these are optional. They may come up again when we get to the chapter on gravitation and orbits, but otherwise, if you don't do astronomical problems, you're not likely to see these very much. Just briefly, let's look at the range of times that are known to exist. The length of the whole age of the universe since the Big Bang is around 10 to the 18th seconds. And then on the other end of the range, the very shortest lifetimes measured for the most unstable and exotic particles are on the order of like 10 to the negative 22 or 23 seconds. So again, 1 second lies sort of in human experience, lies sort of in the middle of that range. By the way, since we're talking about time units, please make sure that you know the conversions between seconds, minutes, hours, days, and years. I recommend that you just memorize these. And I will expect you to know them, actually. And then finally, the range of masses. Masses expand more orders of magnitude than lengths or times. It's roughly 80 orders of magnitude here between the mass of the entire observable universe compared to the mass of a human, compared to the mass of the very smallest particles that are known. Since we're talking about mass, let's spend one slide to just briefly discuss the difference between mass and weight. It's important to disambiguate these two terms. Mass, specifically in physics and in the sciences, refers to the amount of matter that's present in an object. Now, because protons and neutrons individually have about 2,000 times the amount of matter as electrons, I didn't bother to list electrons here. Essentially, the amount of matter is kind of like a count. It's proportional to the number of protons and neutrons that an object has in it, in total. So, what does mass do for an object? Well, it causes an object to be harder to accelerate the more mass you have. So we call that property inertia. So mass is basically a measure of inertia. We'll talk about this in chapter 4. And mass also creates gravitational pull and responds to gravitational pull. So that's weight, is a nickname for gravitational force, which we're about to mention here, and we'll talk about that more in chapters 4 and 6. The unit of mass is the kilogram or the gram for MKS and CGS, or the British unit is rarely used, the slug. Now, weight, on the other hand, is a force. It's not an amount of matter, it's not a mass, it's a force. Specifically, it's the strength of gravitational force that acts on a mass when that mass is near a planet or on the surface of a planet. So therefore, weight has units of force. In the British system, force is measured in pounds. So that's why the tensile strength of fishing line, for example, is measured in pounds. They'll say, oh, this is 12-pound test or 20-pound test line, because that's how much force it takes to break that fishing line. The metric units for force are newtons for MKS or dynes for CGS. So why is it that we sort of have conversion factors between kilograms and pounds. If you look in most everyday stuff, if you go to the supermarket, for example, and pick up a can of food, it will have the amount of pounds or pounds and ounces written on the side, and it will also have the number of grams or kilograms written on the side. Well, because the people who have printed that have made an assumption that that can of food is located specifically on the Earth and near the surface of the Earth, and that you don't care about that much precision because the strength of this gravitational force actually varies a little bit around the surface of the Earth. It varies by about 1 to 2, 0.1 to 0.2%. Okay? So as a result, they make the assumption that we're always measuring weights of things near the surface of the Earth, so therefore we can use these as a proxy for each other. However, if you were to take that same can of food and move it to the surface of Mars, the gravitational force will be about 1/3 as much as it is on the surface of Earth. Or on the surface of the Moon, it'll be about 1/6 as much. Or if you were to take that same can of food and move it far away from any planet, then there will be no force acting on it at all. So please be careful when in physics class not to confuse the term weight with the term mass, and not to confuse the units that are used for each of those as well. Okay, please, at this moment, please take a look at the following 4 questions and try and answer them based on what you just heard, and pause the lecture now. All right, so quickly to review the answers to these, if you were to take a 200-pound astronaut and move him to distant outer space far away from any planet, what would his weight become? It would become 0 pounds because there would no longer be any planetary gravitational force acting on him. In fact, if you move that same astronaut to the surface of Mars, his weight would go down to something like 70 pounds. The surface of the Moon, about 30 pounds. And then distant space, 0. Suppose a different astronaut has a mass of 85 kilograms. This is actually a little bit of extraneous information here. That mass doesn't matter. It doesn't matter that that astronaut is on the surface of the Earth. That mass depends on how many protons and neutrons and how much matter is in the astronaut. It doesn't matter where the astronaut is located. So that astronaut's mass would be 85 kilograms on the surface of the Earth, on Mars, on the Moon, or in distant outer space far away from any planet. It would still be 85 kilograms. So what can you do to change the mass of something? Well, you'd have to add matter or take away matter from it. So if you're a human, you could eat a meal, or you could go to the bathroom, and those would increase or decrease your mass. If we count the clothes on a human, then you could put on some clothes or take off some clothes, or you could cut your hair, and that would decrease your mass as well. You can change the weight of an object, like a person, by leaving them in one location on a planet and then changing their mass. So all the things we just said for the previous question also would change the weight of a person that's staying in the same location on Earth. Or you could take that person and move that person off the surface of the Earth where the gravitational force weakens, gets weaker and weaker as you get farther away. In distant space, the weight would go to 0. Or you could move to the surface of a different planet where the weight would have a different value. So either one would work for changing the weight. There are a lot of quantities that we're going to be dealing with this semester. In fact, the majority of the quantities this semester are going to not be base quantities or fundamental quantities, but are derived quantities, meaning that we take the base units and we multiply and divide them in some combination to make this compound or derived unit. So here are just a few of the many derived units that we're going to be using this semester. And I expand these down below, and you can see exactly what they're made out of. So for speed, we mentioned this earlier. Speed is a length divided by a time. Once you know the dimensions of speed, right, of the physical quantities, then you can just plug in what the MKS or CGS unit or British unit is for length and for time, and you'll wind up with then the unit in that system for speed. So if I plug in the MKS units for length and time, that's meters divided by seconds, that's the MKS unit for speed. The same is true for the CGS unit. Length is centimeters, time is seconds, that's the CGS unit for speed. Density is defined as a mass divided by a volume. Well, we recognize mass as already being a fundamental or base quantity. So we can just plug in the MKS or CGS units for mass. But volume is not a base quantity. In fact, volume is itself a derived quantity. A volume is a length times a width times a height, or in other words, length cubed. So I plug in the MKS unit for length and cube it in the denominator, or the CGS unit for length and cube it in the denominator. And I wind up with kilogram per cubic meter or grams per cubic centimeter as the MKS and CGS units for density, respectively. I should just mention that CGS units are often not used for a lot of quantities, or not used very often. They're used pretty rarely. But density is an exception for that. Density is an example where we use the CGS unit usually more often than the MKS unit, for reasons that will become clear when we get to density several chapters from now. Finally, pressure is defined as force divided by area. We'll learn later in chapter 4 that force is a mass times a length over time squared. Area, I want you to learn right now, area is a length times a width, or in other words, length squared. So I'm leaving this unsimplified for the moment, so you can see what the MKS units are or the CGS units are if we plug them in. And then I'm simplifying it here on the right. So here are the simplified MKS units for pressure, kilogram per meter second squared. Now, pressure is one of these units where we actually have a name, a named unit for this quantity. Okay? It's a mouthful to keep saying or writing kilogram per meter per second squared. So instead we just write the Pascal. Pascal, capital P, lowercase a. And a Pascal is understood to be the MKS unit of pressure, so that means it has to be this. This is the named unit for CGS pressure. Not every compound unit or derived unit has a name. Density has no name, so we just write kilograms per cubic meter. The same is also true for momentum. Momentum, that we'll learn later, has no named unit. But many other quantities, like force and energy and power, do have named units. So we'll learn them as we go. We can use units. We can take either units or the words for the physical dimensions, like length, time, mass, and use them in algebraic equations to perform what's called dimensional analysis. And this is useful for a couple of things. One is, if we encounter an expression, a mathematical expression, a formula, for some quantity that we don't really know, we can use dimensional analysis to try to figure out what that dimensional quantity might be. And the second thing we can do is, dimensional analysis helps us to discover errors or mistakes either in our initial formulas or in our algebra as we go along the way. In fact, most of the time when we solve physics problems, and we're always plugging in the units as we go, we're doing dimensional analysis as we go. Here's an example of the first thing. Suppose that I have a formula like this, an expression that we encounter in a textbook, where I know that g is an acceleration and lambda is a length, but I don't know what c is. Well, I can do some quick dimensional analysis and find out. So here are the units of acceleration. There are the units. There's length. The 2 pi is dimensionless, so I just want you to see it doesn't have any units at all. And then I simplify this and I find, oh, c seems to have units of length divided by time. Chances are it's probably a speed. Once in a while in physics, you might have two different physical quantities that have mathematically the same looking units. An example that we're going to see later this semester is energy and torque. Both of those reduce mathematically to the same dimensional units, but they're actually very different physical quantities. However, that's pretty rare. And if we see a length divided by a time, it's probably a speed. Here's an example of the second thing where we can catch a mistake. Notice that the left-hand side of this equation is pressures, a difference between two pressures, and the right-hand side here has densities times speed cubed, density times speed cubed. So suppose your friend writes this down, you're working on a fluid flow problem, you're using Bernoulli's equation, your friend writes this down, and then you start plugging in values and working. And you might discover that as you plug in all of your numerical values with their units, you find that the left-hand side here has units of kilograms per meter per second squared, look at the previous slide here if you want to see the units for pressure, density, and speed. So that was the unit of pressure from the previous slide. And then on the right-hand side, when you take the units of density and speed cubed and simplify that, you get kilograms per seconds cubed. Uh-oh, that's not good, because the left-hand side here has different units than the right-hand side, so how can they be equal? They can't. Whenever you're going to add two quantities, subtract two quantities, or equate the two quantities, they must carry the same units. They must. Otherwise, it's logically inconsistent. It's forbidden to add, subtract, or equate two quantities that have differing units, okay, like a mass and a length. So in this case, chances are the initial formula had a mistake, and indeed it did. So I'll give you a hint. It has something to do with the powers on the two speeds right here. But I'll let you try and figure out what those powers are supposed to be. They're not supposed to be cubed. Finally, there's one more shorthand for us to learn, and that is the use of metric prefixes. So the metric prefixes give us a more compact way of writing the quantity times 10 to the some exponent, whatever that might be. So you'd think this would already be pretty compact, but it turns out that we use these so often that we prefer an even more quick and easy way of denoting them. So if you look in this table over here, here's a list of powers of 10. Here are the exponents written a little larger just for ease of reading. And these are the metric prefixes that we use as an abbreviation for each of these powers of 10. So for example, for 10 to the 6th, that's a million, we can abbreviate times 10 to the 6th by using instead the prefix mega in front of the unit's full name, or the letter capital M in front of the abbreviated unit. So here's a bunch of examples over here on the left. Suppose that I wanted to abbreviate times 10 to the 3, and I have some quantity that is times 10 to the 3 meters. So I come over here to my chart. 10 to the 3 is abbreviated by kilo if I'm using the full words, or just the letter lowercase k if I'm using the abbreviated unit. So sure enough, if I have the full word meter, I just put a prefix of the word kilo on the front. Notice there's no space or other punctuation. If I'm using just the abbreviated unit for meter, then I use just lowercase k. Again, no space or other abbreviation or other punctuation. Millivolt times 10 to the negative 3, pardon me, if I want to abbreviate times 10 to the negative 3 volts, then I go down to the chart here and I see that that is milli with lowercase m. So when I go back over here, millivolt if I'm using the full words, or if I'm using the letter lowercase m right in front of the V. Many units are just a single letter, so then you just wind up with two letters side by side. The first one is a prefix and the second one is a unit. You just learn to recognize these over time. You'll tend to, you learn to take this apart and recognize, oh, this first one is probably the metric prefix and the second one is probably the unit itself. However, we have a lot of units that use two letters like this, Pascal, Hertz, electron volt, or even three letters sometimes or more, right? Like slug or min, M-I-N for minute. In that case, you still keep the whole unit abbreviation, and again, you just use the one-letter metric prefix abbreviation. Looking down the list, we see that most of these prefixes exist for multiples of 3. In fact, they go all the way up to 24, and they go all the way down to negative 24 in the other direction. The only exception is where we have prefixes for every power of 10 is between 1,000th and 1,000. In other words, for exponents between negative 3 and 3. I recommend that you memorize all of these in the red box. While it's good to know some of these other ones, because these are used in computer science more and more, like petabyte and exabyte, but the ones that you're most likely to encounter are tera through pico. And I'll assume that you have memorized these. So these are the ones that I will use on things like exam questions. The one that you're least likely to encounter is deca. We probably won't even use it once this entire semester. But hecto, deci, and centi are used pretty frequently with particular units. So you'll encounter them in other classes and daily life. Deca, by the way, is 2 letters. I should just point that out. There are a couple exceptions on this list. One of them is that deca is 2 letters instead of 1. But again, we'll probably not use that. And one of them is a Greek letter, right down here. I'll end by saying that notice how capital letters and lowercase letters make a difference in the meaning. Milli is a lowercase m, and that means 1,000th. But a capital M turns it into mega, which is a million. Another example is capital P is peta, 10 to the 15, but a lowercase p is pico, which is 10 to the minus 12. So it's really important. If you're used to mixing your capital and lowercase letters in your as you do normal handwriting, all right, that's fine, but when it comes to writing your units, you must distinguish. You have to be very careful not to do that. So please learn to distinguish capital from lowercase letters. Try writing your capital M's and your lowercase m's, or your capital P's and your lowercase p's in a distinctly different way. And that's important. This is also important for units themselves as well. So finally, let's end this lecture with examples of how to convert units. Suppose we have a quantity like 24 miles. This is a length. And suppose I want to convert that into a different length unit, in this case kilometers. Well, the 3 steps that I use are this. First, go to a table of length conversions and find a conversion that relates kilometers to miles. And there are 2 that you might find. Usually, they'll have 1 mile equals so and so many kilometers, or they'll have 1 kilometer equals so and so many miles. Either one of these would work with the rest of this method. So I'm just going to go ahead and pretend that I looked at the table and I saw the one on the left. So let's work with that one going forward. However, the whole method works for the one on the right also. Step 2, take that equation, that simple equation right there, divide both sides by 1.619 kilometers and turn it into this equation on the left. And then again, divide both sides by 1 mile and turn it into that equation on the right. So now we've created equations where there's a 1 on one side of the equation. Now, why is this important? Well, because when you multiply something like 24 miles by 1, you don't change the length of that physical quantity, or the size of that physical quantity in any way, right? If you multiply 24 miles by 1, it's still 24 miles. And you can multiply it by 1 as many times as you want. So I could take 24 miles and multiply it by this ratio over and over again, 2, 3, 4 times, or that ratio. So it doesn't matter, and I haven't changed the length of 24 miles. This is important because that means that whatever number of kilometers this is, it will have the same physical length through space as the original 24 miles. Now, the next step is then to choose which of these 2 conversion factors now. We're going to take this ratio here, and we're going to call this a factor because we're going to use it for multiplication. Which of these 2 conversion factors is going to give us the desired outcome? And what that desired outcome is to cancel out the units that we don't want, which in this case is miles, and leave us with the units that we do want, which in this case is kilometers. Well, let's start with the good example, and that is the conversion factor on the right. If we choose this conversion factor on the right and multiply it against the 24 miles, look what happens. The miles cancels out and disappears, and we're left with kilometers in the numerator, which is exactly what we wanted. Great, so that's the answer. So we wanted to use this one here on the right. Just for good measure, let's see what happens with the one on the left. If we multiply 24 miles against this conversion factor here, then we find that we wind up with miles squared in the numerator, and we have kilometers in the denominator, which is not what we want at all. Technically, this quantity here is still 24 miles, but it doesn't really look like a length at all. And this is not the units that we wanted. So that's the wrong choice. All right. Then once you see that your units are going to come out the way you want them, then the last step is take out your calculator and multiply 24 times 1.609 and get that answer. By the way, I round this off here I see that the initial 24 miles looks like it has two significant figures, so I rounded my final answer off to two significant figures. Quick little side note, if you're looking up conversions, make sure you look them up to at least the number of sig figs of your initial value that you're converting, but good practice is to go at least one more or two more significant figures beyond that. So if you have a two significant figure initial value, then make sure your conversion factor is good to 3 or 4 significant figures or more. You'll find that many of the conversion factors we use are perfect. They have infinite precision. They're exact. Okay. Let's look at 2 more examples. This one involves a unit that is a ratio, and this was a speed, right? Kilometers per hour. It's length divided by time. Suppose I want to convert both the length and the time to new units. So we can do all of this in one calculation. First, I go to a table of conversions for lengths, and I look up a conversion from kilometers to meters, or vice versa. I could find also 1 meter is equal to 1,000th of a kilometer, and that would also work. But I'll just stick with this one. I turn that conversion into 2 conversion factors, and then I examine those 2 conversion factors to decide which one is going to cancel the kilometers and leave me with meters in the numerator. I do the same thing with a table of conversions for time. And I find a conversion between hours and seconds. I create 2 conversion factors from that. And then I use inspection to decide which of these 2 conversion factors, when multiplied against this speed right here, is going to cancel the hours and leave me with seconds in the denominator. So at this point, take a look yourself, pause the lecture, and decide which of these conversion factors to use. Okay, I hope that you chose these 2, and let's do the algebra and find out. So when I multiply 120 kilometers per hour by the first conversion factor, I see that the kilometers cancels out, leaving me with meters in the numerator. Great, that's exactly what we want. When I multiply by the second conversion factor over here, I see that the hours cancels out from the denominator, and it leaves me with seconds in the denominator, which is also what I want. The last step I do is I take out my calculator and I calculate the numerical values. 120 times 1,000 divided by 3,600, and I get this repeating decimal here, 33.3333. I look at my original value. This 120 was probably 2 significant figures, so I'm going to round my final answer to 2 significant figures. Okay? By the way, looking from the start, look at the number of sig figs. Make sure your conversions have at least that number of sig figs. In this case, both of these conversions are exact. So they have infinite precision. They have an infinite number of significant figures. One last example. Let's convert a volume. So here we have 5 cubic meters, and I want to convert it into cubic centimeters. Now remember, a volume is a length cubed, and an area, which we don't have here, is a length squared. So I want to go to a table of conversions for lengths, if you don't have one explicitly for volumes. And I find this conversion, 1 meter is equal to 100 centimeters, or I might find that 1 centimeter is 100th of a meter. Using this one, I can create 2 conversion factors, and I'm going to want to choose the one of these that will cancel out meters from the numerator and leave me with centimeters in the numerator. So take a look at those 2 and by inspection decide which one to use. Pause the lecture. Okay, I hope that you chose this one. And you can see that if we multiply it against the 5 cubic meters one time, look what happens. 1 power of the meters will cancel, leaving meters squared. And we get multiplied in the numerator by 1 power of centimeters. So now I have meters squared times centimeters. That's great. That took me 1 step in the direction I want to go. But I need to cancel out all 3 of the factors of meters. So I need to multiply by that same conversion factor 2 more times. And then that means I collect 3 factors of centimeters in the numerator, leaving me with centimeters times centimeters times centimeters, which is centimeters cubed. Then I take out my calculator and I calculate the numerical value. 5, or this one you can do in your head. 5 times 100 times 100 times 100 is 5 times 10 to the 6th. Now, after you've done a lot of conversions with areas or volumes or other squared or cubed quantities, what you might prefer to do is to write this in a more compact notation. Notice that you can take all three of these conversion factors here and just write it more compactly as one conversion factor cubed. But let me just warn you to make sure, notation-wise, that you have big parentheses around this factor and the cubed is on the outside of that parenthesis, so that way you know that it applies to everything that's inside. And then you have to remember algebraically to do exactly that. So what that means is this cube applies to the meters, making it meters cubed, so this cancels the units. The cube applies to the centimeters, this becomes centimeters cubed. And then finally the cube applies to the 100, meaning this is 100 cubed, which is 10 to the 6th. Just checking significant figures, this had 2 significant figures on the original value, so I write my final answer to 2 significant figures as well. And I check that my conversion factor itself had at least 2 sig figs, which in this case it's exact, so it has infinite precision. All right, that's the end of this lecture. So please use use the things we just covered to practice problems on tutorial 2A until you feel comfortable, and check your answers against my solutions. And once you're comfortable with the stuff we've covered, please do the problems for credit that are on online homework number 2 covering units.